Voltage dropped in circuit conductors may result in low voltage at the electrical load. Circuit design may include calculations for identifying and correcting voltage drop issues. The first voltage drop video identified the components of a circuit that causes conductor voltage drop. This video, Part 2, presents voltage drop examples and solutions to correct voltage drop issues. The voltage drop formula shown here solves for the voltage dropped in the circuit conductors. Let's review each component of the formula. The length of the conductor supplying the load must be known. This value is doubled because there are two conductors supplying the load. The current of the load must be known since the load current affects the voltage drop. The constant resistance value of 12.9 ohms is used for copper. The size of the wire supplying the load must be identified since different conductor sizes affect the voltage drop. The completed formula results in the total voltage dropped in the conductors. The voltage dropped in the conductors is subtracted from the voltage source to solve for the load voltage. The circular mill identification is in reference to the size of the conductors supplying the load. A circular mill is basically a reference to the area of a conductor. The larger the conductor, the more circular mills. The circular mill listings of common size conductors can be found on multiple websites. The National Electrical Code lists the circular mills for standard conductor sizes. This table lists the conductors from smallest to largest and their associated circular mill value. Let's focus on a few of these circular mill values to demonstrate voltage drop problems and solutions. The purpose of calculating the voltage dropped in the conductors is to find the voltage at the electrical load. So, what is the acceptable voltage at the load? There is some electrical equipment that specify the minimum voltage at the load. However, if not specified, a general rule for the maximum voltage dropped in the conductors is 5%. That is to say that 95% of the supply voltage must arrive at the electrical load. A 5% voltage drop will be used for calculations on all of the examples shown in this video. 5% of 120 volts is 6 volts. This means that 114 volts must arrive at the load. 5% of 240 volts is 12 volts. This means that 228 volts must arrive at the load. Let's solve for the voltage dropped in the conductors in the example shown. The supply voltage is 120 volts. The distance between the power supply and the load is 100 feet. The current of the load is 22 amps. The load is supplied with a number 10 wire. The length is multiplied by 2. This is multiplied by the current, which is 22 amps. This is multiplied by the constant value of copper, 12.9. This value is divided by the circular mills of a number 10 wire, which is 10,380. The voltage dropped in the conductors is 5.46 volts. This is an acceptable value since it is less than a 5% voltage drop. The next two examples show how an excessive voltage drop can be corrected by using larger wire. In the example shown here, the load is located 150 feet from the source voltage. A number 8 conductor is used to supply a 36 amp load. The number 8 conductor has a circular mill value of 16,510. These values result in a voltage drop of 8.4 volts. This is more than a 5% voltage drop. Let's examine how using a larger conductor reduces the voltage drop. In this example, notice that the number 8 wire has been replaced with a number 6 wire. Notice that the circular mill value of a number 6 conductor is 26,240. The result is a voltage drop of 5.3 volts. Using the number 6 conductor results in a voltage drop that is within the 5% voltage drop range. The most common way to correct voltage drop problems is by using a larger conductor. A conductor size can be calculated using a specific voltage drop. Notice the change in the formula. A voltage drop value is used in the denominator of the formula to find a circular mill value of the conductor. The formula still requires the length of the conductor and the current of the load. Using this formula results in a circular mil value. The circular mil value is then be referenced to a conductor size. In this example, 6 volts is used as the voltage drop. The load is located 75 feet from the voltage source. The load is 58 amps. Using these circuit parameters, the conductor circular mil for this circuit is 18,705. Notice in the circular mil table that a number 8 conductor has 16,510 circular mils. A number 8 conductor is not large enough. A number 6 conductor is used since a number 6 conductor has 26,240 circular mils. Let's examine a 240 volt circuit. In this circuit, the load is located 200 feet from the source voltage. The load is 75 amps. Number 4 conductors are used to supply the load. Using the formula, the distance is multiplied by 2. This is multiplied by the current of the load. This is multiplied by the constant of copper, 12.9. This value is divided by the circular mil value of a number 4 conductor. The result is a voltage drop of 9.3 volts. 9.3 volts is less than a 5% voltage drop. The number 4 conductor can be used to maintain a voltage drop of less than 5%. Voltage dropped in 3-phase circuits can be calculated. Notice the change in the formula. Since 3 conductors supply the 3-phase load, the number 2 is replaced with the number 1.732. The length of the conductors, the current of the load, and the circular mils of the conductors remain the same in the formula. Excessive voltage dropped in conductors will result in a low voltage of the electrical load. Low load voltage may damage or destroy electrical equipment. The distance between the source voltage and the electrical load may need to be considered when designing circuits. Excessive distances will result in large voltage dropped in the conductors and low voltage at the load. Calculating voltage drop will assure that the correct conductors are used to prevent excessive voltage drop.